All right, for those of you online, for the thing you see there, let's find the hoop and axial stresses on this tank and then show them on a sketch. Okay, so we want to find the hoop and the axial. Okay, and I'm using equations 61 and 62. All right, so we got the pressure, the radius. Remember to use the radius, not the diameter, and the wall thickness. And when you do that, why don't you go ahead and pause the recording if you're online, and then just run the numbers, and let's see what we got. Okay, so the hoop is 384 megapascals, and the axial is 192 megapascals. Okay, and then the next thing we want to do is find epsilon x, epsilon y, and the shear strain, gamma xy. That'd be the next thing to do. All right, and you have the material properties up there, and then you also have the stresses that you just found. Now you do want to put those on a sketch. You know, I always want to be thinking that way. Remember that the hoop is 384. And the axial is 192, so that's 384 megapascals, and that's 192 megapascals. So we good with that? And then we got to the strains, all right, did we? So, and while we're talking about the stress there, what's the shear stress in the XY directions on that thing? Right, it's not much, because on a pressure tank, it's just like a balloon in the X and Y directions. It's being stretched. There's no shear, okay, in the X and Y directions. Okay. All right. So what we got here now is we've got inputs into these equations we can use. So we got that, sigma X and sigma Y. And then we can go ahead then and find the strains in the X and Y directions. Okay. And what do we got? We got epsilon x, and what we're doing is using the Hooke's law equations for these. Okay. So that's 1 over E sigma x minus nu sigma y. And when I ran that one, what did I get? Is that 0.144, is that right? Is that good? Okay. Y'all getting that okay? You good? We run that? What's the units on that? There aren't any units, because strain is a proportion of deformation to original length. We're doing all right? We good? Okay. And then what do we got there for epsilon y? Okay. Again, unitless. Now, in the, wow, that's huge. That's a lot of strain. I didn't realize I made it that big, but anyway, we'll just go with it, okay? So that's a lot. That's 43% strain. You know, there's no metal going to handle that without failing, but we'll say this thing's, we're going to deal with something that's made out of some synthetic that can handle that. All right. Now, how about what's gamma xy going to be? Yeah, because tau xy is 0. Gamma xy is tau over g. Okay, that'll be 0. So we good with that? Okay. So what we just did, we looked at a pressure tank. We did the pressure tank formulas. We got to the stress in X and Y directions. Then we did the Hooke's law stuff. We got to the strains in the X and Y directions. So let's look at a problem now, and we're going to substitute some values in here. And we've got epsilon x is 0.144, and we got epsilon y is 0.432. So let's go to problem 235. That's in your book, of course. And that's a setup. Now the numbers there are different, so I would like you to take the numbers we just derived and put them in to that problem. So this is problem 235. It's on page 15C is where it's at. We good? And just cross out epsilon x and epsilon y and just put the new values that we just found for them in there, if you would. Right. Now let's go ahead and run through this. Let's just spend a few minutes on this and see what we can do with it. So what we have here is now this is stamped on a pressure tank. It's a perfect circle. Okay, it's a logo. And it's got a circle in it with a V in it, so it has the letter V. And the name of this company is Perfect V Pressure Tank Company. Okay, and this is their logo. And they've had this startling realization after they made 10,000 of their tanks and they've stamped their logo on there. They're going, oh my gosh, when we pressurize these tanks, what's going to happen to our logo? So they've hired us to figure out what's going to happen to their logo after they've pressurized their tanks. So let's figure out what's going to happen to their logo, okay? And what we're going to do is we're going to use the center of the tank as our reference point. And what we're going to want to do now is to find strains in the different directions. And I think in a box there, of course I've got so many versions of this thing, I'm not quite sure what I've got out there, but I'm pretty sure I've got a little box there that asks you to find some things. Okay, so why don't you find those things for this tank, and then let's see if we can apply those things to our sketch and come up with what's going to happen to that perfect V. Is it going to be a perfect V anymore? That's the problem we've got, because obviously we've got so much strain going on here, this thing will change shape. All right, so go ahead and find those things that are in the box. And I will give you a hint that this is a rather symmetrical situation. It's not like, there's things that are going to happen repetitively at these different angles because this is a very symmetrical situation. So here's what should be in the box. And if we get all this stuff figured out, we should be able to figure out or have some idea what's going to happen to this shape after the tank is pressurized. So we need to find these 8 things. And also I'd like to know what's the new angle for that V. All right, so I'll probably pause the recording here for a second for those of you online. So see what you can do to start figuring those things out. You've got the formulas, of course. We're engineers, so we've always got the formulas. The formulas are on the back, okay? And their formula is 71, 72, and 77. And I will give you a hint that there is a lot of symmetry here, so you may not have to be running every number. You might be able to assume some things once you run a couple of the numbers, okay? So 71, 72, and 77. So I'll pause the recording. What's that now?
We were ended up the answer, but we were doing that. I didn't take it over.
Okay.
I was like, I got 0.28. He's like, well, I got 0.144, but I was doing straight.
Okay, well, good. You got it covered. Okay. All right, so what we did here, we looked at formula 71, we got the right-hand side, and it's the same for every angle. And here we're going to have 0.144. Okay, now why don't we just stop for a second here and have a look at, let's kind of go off into more of a common sense mode here. We're pulling this way on that figure, and we're pulling that way, right? Now, how does the X pole correspond? Is it bigger or less than the Y? It's less, right? Because epsilon X is less than epsilon Y? Y'all okay? So we got a smaller pole going that way. Now, what kind of shape do you think that thing's going to pull into when we do that? It's going to be kind of an oval, and I don't know, we could look at it, it might be an ellipse, I don't know if it's something that precise, but an oval, right? And it's going to be longer in the X or Y directions. And so it's going to do something, like that, right? You all good? It's going to pull out in both directions. Now, what's the effects of that point? It's going to get pulled out, but also it's going to get pulled more up, right? Then it's going to get pulled more up than it is out. You all good with me there? So that's going to rotate that point, isn't it? And this is a positive alpha, meaning counterclockwise rotation. And sure, that seems to make sense, doesn't it? Because I'm going to end up somewhere up there with that, just from a common sense perspective. Now, what do you suppose the sign is when I do alpha for 135? It's going to be negative, eh? Because that means clockwise. See what's happening there? A little bit left, quite a bit up. And so, I'm sorry, I'm here. A little bit left, quite a bit up. Whoop, one more try. Here we go, I got it. Okay. That thing's going to pull up that away, right? Good? And see, I always like it when I run the numbers and then I do some common sense. When those things agree, I start feeling a little bit better about what I'm doing, right? Okay. All right. So I think this is going to be a negative 0.144. How about at 225 down here? What do you suppose the sign will be? Yeah, why positive? So kind of over that away. Counterclockwise. Good. Okay. And then the last one, I think the smart money's on negative. Okay. We're good. All right. Now, how about anybody run the shear strain at 45? Yeah. Okay. Positive, right? Okay. 0.288. So we good with that? Okay. Now, if that's the deal here, what happens to that angle at 45 degrees? Going to get smaller. Does that make sense? As both those points pull up more than they pull out, this one's going to go up, that one's going to go up, but they're going to go up more than out. So yeah, it's going to make that angle a little smaller, isn't it? Okay. Y'all good? Okay. All right. Okay. Now, let's actually plot this up because, if we're doing this for a client's going to want to know what's really going on, okay? So let's figure out what's really going on. Let's kind of start these one at a time and see if we can get this plotted. Let's start with an easier one, and then we'll go from there. Let's start with epsilon x. Okay? Epsilon x is a positive 0.144. Now that means that it's going to get 14.4% longer in the x direction. Good? Okay. Now, how many boxes do we have? Now this is our reference right here. That's where we're going to start, from the red dot. You kind of, when you're doing this deformation stuff, you have to declare a reference is what you got to do. All right. All right, now how many boxes do we have that make up the radius? 1, 2, 3, 4, 5. Good. So if I go from that reference out to this point at 0 degrees, it's 5 boxes. So one radius, so the reference is in the middle, one radius equals 5 boxes, small boxes. So what is one box then? What percentage of strain is it? One box. 20%? Good. Because I got 5 boxes in the full radius. I'm starting at my reference point in the middle. I'm going out to the edge of the circle. That's 5 boxes. Each box is 20% of the total. We good? Okay. So that's 0.2 strain. Good. All right. Now, given that, why doesn't everybody plot up where this point that I've circled, the point over here that I've circled, where is that point going to land after those strains occur? Okay. Each little box represents 20% strain. Where is that going to be? And you do have to kind of declare a reference point. When we did the rectangular one, we said the reference was in the lower left. That's by reference, I mean a point that does not move, it doesn't deform. On this one, I'm going to say the center is, because it's a circle. That's the most logical place to pick as my reference point. Everything expands out from there. Okay? Y'all okay? Good. So where's that point going to end up? That the point at 0 degrees. How far out? How many boxes out? 3/4 of a box, roughly. Yeah, okay, we good? Because a full box is 0.2. We've got 0.144. We're roughly 3/4 of 0.2. Okay, so that's going to be right about there. Okay. How about on the other side? What do you suppose is going to happen? Similar thing, right? Because we're symmetrical. So plot up the other point. We good? Now we got no shears at 0 degrees, so it's not going to swing left or right or up or down. It's just pulling straight out because it's all normal stress in that direction. Right? Now how about up down? Why don't you plot up at 90 and 270 degrees where those points are going to be? So look at the strain in the y direction. Use that to plot up that point at the top and the point at the bottom, where they go. Look at the strain that we calculated in the y direction. Okay. 0.432. 2 boxes, a little bit more. Does that sound about right? Okay. So up there and right there. Okay. And why don't I'll do these in red just so they show up a little better. So see what I'm doing now is I'm predicting where those cardinal points are going to end up. I can almost start to sketch in what that thing's going to look like now, okay? But to get a little bit better definition, let's look at the 45s. Okay, and notice how I kind of created that grid paper. You've got boxes going at 45s also. So take the one at 45 degrees. Look at that normal strain. Let's start with that. And then run that out to its position. So look at the normal strain at 45 degrees. Plot that point up, okay? right there at 45. What's the normal strain at 45? Yeah, same sort of thing, just count boxes. Okay. Now, that's not the whole story though. There's a little bit more going on at 45. But that's a start, okay? 45 degrees, about 0.288. All right. So one box is 0.2, a little less than a box and a half. Is that about right? And that's going to happen every place, right? So there we go. Like that. And see, that's already looking about not too bad, isn't it? I mean, see how that's kind of fitting in the curve in there? If you run AutoCAD, there's a nice little command called spline that kind of creates a curve that fits points. You can fit that in there pretty well, huh? All right, but there's more to it. And actually, it's going to, I think, make for a little bit better situation. Maybe not, I don't know, we'll see. Now, that not only will that line stretch out, it's also going to rotate over. And that's alpha. Alpha is how that line rotates. Positive is counterclockwise, negative is clockwise. Now, see, this is an angle in radians, but it's also approximately equal to the tangent of the angle, and that's going to be the ratio of the two sides of a right triangle there. So we can basically go with this, that 0.144 is that how much it kicks out perpendicular to the line. Okay? It's not a perfect match, but it's pretty good. Okay? So once again, we can just count boxes and get where the final position of that point will be. It's based on alpha. All right, so that's a positive, okay? And with alpha and also with gamma, you can use this idea that it's measured in radians, but it's also a ratio of two sides of a right triangle. It's a tangent is what it is, okay? And based on that, you can figure out how much the kickout is, because we're assuming that's 1 unit, which is 5 boxes, so we can figure out how far that kickout will be right there. So what do we got for alpha? It's 0.144. So about how many boxes is that? 3/4 roughly? You all good? Okay. So that's going to put it right about there for the final location. We good? And how about now, see how the other one's going to rotate? It's negative, the one on the left. The one at 135 degrees is a negative alpha. That's going to go clockwise. So that's going to end up over there, right? And then this one is counterclockwise, so it'll end up here. This one's clockwise, so it'll end up about there, all right? So now we've got a pretty well-defined shape. And see, that makes a pretty nice figure. And I don't know what kind of figure it is, if it's an ellipse or what the heck it is, but it's, you know, it looks reasonable, doesn't it? Okay. So if you, and you know, if I were doing this for real, you know, I'd probably calculate these. I'd probably create a spreadsheet that just ran the numbers for me. I'd plug in every 10 degrees. I'd plot those points up, and then I'd connect them with a spline and run it that way. I mean, that might be a reasonable way to do it, okay? And you'll get the final shape. So after this tank is pressurized, and I'm not doing a very good job drawing here, this is probably what it ought to look like. Something like that, okay? Okay, so that's just a little bit on a number of topics. So we did the stuff with strain, went from strain. So we did the stuff with a pressure vessel, we went to pressure vessel, we went to stress. With the stress and the material properties, we went to strain. With strain, we can predict deformation. Okay? And I keep mentioning this, but that one student with that conveyor belt with the rollers, this would be a perfect way to look at that. You could then look at how wide that thing is, especially in the X direction, and see if you're going to get interference with the other roller when the things start to roll. All right? Even though we're doing a different problem here with a pressure vessel, but you can get the concept. All right. All right, we got a couple minutes here. What you predict? What's this? We have this perfect V, right? It's a 90-degree V. What angle is that thing going to make? Just take a couple minutes to think about this. What angle will that V end up being after this thing's pressurized? It's not going to be 90 degrees anymore. What will it be? Okay, just think about that for a second. We'll give it a few minutes, see what you can come up with on that. What's the final angular measurement here going to be? Right in there. You got a protractor, it's one way to do it. Kind of funny too, because sometimes you get through the engineering education, you laugh at doing stuff like that, but it's probably the best way to do it. If you don't want an angle, just put a protractor on the thing and read it. I mean, I can't think of a better way to get an angle than that. We always like doing our calculations, but hey, measure the angle. Anybody got a protractor? When you use a protractor, what are you all coming up with for that new angle with a protractor? I'm sorry?
79. 79?
Is that good?
Yes.
You know, it's plus or minus with a protractor, right? Okay. Okay. Is that in the ballpark? Yeah, okay. All right. Now, how do we calculate it? What's the number we would use to calculate how much that angle is going to change? Yeah, shear strain. Shear strain is an angle in radians. Positive angle means the angle, a positive shear strain means the angle gets smaller, right? Because what we're doing essentially, we're taking an element that is at 45 degrees. See, so we're doing a little square element like that, and then we're seeing how that lower left-hand angle is changing. That's what we're doing. All right. So what do we got? We've got 90 degrees is pi over 2 radians, and it's going to get smaller by that amount. I don't know, what does that come out to be? Oh, 73 and a half? Oh. Okay. Okay. So, and then what's the radian measure? Yeah, 1.28, something like that. Okay. And that's about 73? 73.6 or something? I don't know what it is. 73.5 degrees? Okay. Well, we get a little air there, but it's awful big deformations. We're fine. Okay, no big deal. All right. So I'm just trying to illustrate this idea of strain and some of this things we can do here now. Okay. All right. All right. So we've done this deformation stuff 3 different ways. We've done it with a rectangle once. We did that in class. We did it in homework. We just did one with a circle. And then we've also done those schematic sketches that you dimension, but those are just 3 different ways of looking at it. Okay. All right. Why don't I get you a couple pressure vessel strain things to work on here. About 251 and 253. And why don't we do one extra little thing here? Let's see. So 251. Now have a look here. 251 is on page. It's on page 17. So I just want you to find the stresses on the two tank walls. So what I want you to do on 251 is find sigma AB and sigma CD. Okay, and I'd also like you to do 253. And on that, I'd like you to do one extra thing. Find the find the shear stresses on the welds too. So find tau. What we got? Tau weld 1 and tau weld 2. So you're gonna find the stresses on the welds. So we're going to find sigma weld 1, but also the shear on weld 1, and sigma weld 2, and the shear on weld 2. So what we're doing here is we're just doing a little biaxial stuff. Okay. So that's what I'd like you to do there and these will be due Friday also, okay? And that is the 14th. All right. Good to go? Okay.
I have a quick question on these the welds.
Uh-huh.
So when we use the formula